All right, welcome back, Ravens. It is time for part three. We're halfway through. It's time for the metals. We are looking at the specific special named groups. There are certain groups that we all want to know the names of. So, start us off. Important groups of the periodic table. Groups are designated by number, and important groups have a name. The name is not printed on the periodic table, okay? And these groups have distinctive physical and chemical properties. Okay. You're going to need more colored pencils. If you don't have them with you, pause and go get them. All right, the first thing I want you to do is take that periodic table. It was page 67 in your binder, the first page of this notes packet, and I want you to color code or somehow label each section. This would be something good for a note card for a test to know the location of each of the named groups. Okay, pause so you can get that done. For the sake of the video, I'm going to keep going. All right, first we start with the alkali metals. They are group 1. They are very reactive, extremely reactive, explosively reactive, especially with water. One electron in their outermost shell, so one valence electron, and they form positive 1 ions, smaller than the uncharged. Ignore that part. You don't need to know right now. Okay. All the alkali metals are soft and with a low density, okay? They're kind of like the consistency of hard butter when you take it out of the refrigerator. Okay, let's watch a video on alkali metals. Come on. There we go.
The alkali metals are soft metals that tarnish rapidly, even in dry air. They have lower melting points and lower densities than most other metals. They all react violently with water, and as a result are never found uncombined in nature. Lithium is the least dense of all the metals. It is sometimes used to make lightweight steel alloys for high-performance aircraft. Sodium is the sixth most abundant element on Earth. Its many uses range from table salt to batteries, and it is one of the main components in seawater that makes it undrinkable. Potassium is the seventh most abundant element on Earth. It goes into glass, soap, and explosives. Rubidium is used in photoelectric cells, vacuum tubes, and heart research. Cesium, a rare element, particularly reacts with other elements. Scientists use it to help calibrate atomic clocks. And francium is possibly the rarest element on Earth. It is very short-lived and occurs as a radioactive byproduct of uranium decay. There is less than 1 ounce of francium in the Earth's crust at any one time. Like most other metals, the alkali metals are silvery metallic solids. They are excellent conductors of electricity and heat. The alkali metals are very reactive, and they easily form compounds with other elements. These compounds are generally alkalis, which are capable of neutralizing acids. Because they are so reactive, the alkali metals are never found uncombined in nature. In their pure forms, the alkali metals must be stored under oil or kerosene to keep them from interacting with oxygen or water vapor in the air. The alkali metals are as soft as cold butter and much less dense than most other metals. Lithium, sodium, and potassium are even less dense than water, so they will actually float. Coming into contact with water, alkali metals interact to form oxides or hydroxides, hydrogen gas, and heat. When lithium is placed in cold water, it melts quickly and moves around the surface of the water, fizzing. And this reaction becomes increasingly violent as you go down the group of alkali metals. Cesium is so reactive that it explodes when exposed to water. Looking at the periodic table can help explain the reactivity of the alkali metals. On the periodic table, the elements are listed in order of their atomic number. The atomic number represents the number of protons in an element's nucleus. In its normal or ground state, this nucleus is also surrounded by an equal number of electrons. And as the atomic number increases, generally so does the size and mass of the atoms. As you read the table from top to bottom, each horizontal line is called a period. Each period represents the number of electron shells the element's atoms normally have. For example, there are 4 electron shells in an atom of potassium, so it lies in period 4. Meanwhile, an atom of cesium in period 6 has 6 electron shells. As you read the table from left to right, the vertical lines of elements are called groups. Elements in a group have the same number of electrons in their outermost electron shells. These outermost electrons are called valence electrons, and they dictate how elements interact. Elements in the same group generally interact with other elements in similar ways. None of the elements greater than atomic number 83 are completely stable. All of these elements, including francium, are radioactive. All alkali metals reside in group 1 because they each have only 1 electron in their outermost electron shell. Because atoms need 8 electrons in their valence shell to be stable, the single valence electron in the alkali metals makes them very unstable, and they easily lose this electron to other elements. Generally, as you move down through a group, the atoms' hold on their valence electrons becomes weaker. So as you move from lithium to francium, each element is more reactive than the one before it.
All right, moving on. Next, group 2 are the alkaline earth metals. Okay, so we have group 1 are the alkali metals, and group 2 are the alkaline earth metals. They're also very reactive, but not as bad as those group 1s, not like those alkali metals, but they're very reactive. They have 2 electrons in their outer shell, so 2 valence electrons, and therefore they will form positive 2 ions. Okay, and the video explains it much better than I can.
The alkaline earth metals are generally softer than most other metals, and they react readily with water, particularly when heated. Each has 2 valence electrons in its outermost electron shell. They are powerful reducing agents that readily give up electrons to other substances. The element beryllium can absorb large amounts of heat, which makes it useful for spacecraft and aircraft construction. Magnesium is a light metal. It is combined with other metals to make racing bicycles, airplanes, missiles, and other products that need to be lightweight and strong. Calcium is an essential element for countless living organisms. It forms the foundation for everything from shells to teeth and bones. Strontium goes into colorful flares and fireworks, and phosphorescent paints. A radioactive version of this element is one of the most deadly byproducts of nuclear fallout. Barium is a heavy silver metal that is used in spark plugs, vacuum tubes, and fluorescent lamps. And radium is an intensely radioactive element that doctors once often used to destroy cancer cells. In their pure forms, the alkaline earth metals are shiny silvery gray metals. They have relatively high melting and boiling points, and they are good conductors of heat and electricity. These metals have a gray-white luster when they are freshly cut, but they tarnish quickly when exposed to air. The heavier members of the group tarnish especially quickly. Beryllium, the lightest of the alkaline earth metals, is hard enough to scratch glass. But barium, the heaviest, is only slightly harder than lead. The alkaline earth metals react readily with water, especially when they are heated. They combine easily with other elements, and as a result, are never found in their pure, uncombined forms in nature. Although they are harder, stronger, and denser than the alkali metals, they are nearly as chemically reactive. The alkaline earth metals are so reactive because they are very electropositive. This means that, like the alkali metals, they easily lose electrons to other elements. Let's take a closer look at the periodic table. On the periodic table, the elements are listed in order of their atomic number. The atomic number represents the number of protons in an element's nucleus. In its normal or ground state, this nucleus is surrounded by an equal number of electrons. And as the atomic number increases, generally so does the size and mass of the atoms. As you read the periodic table from top to bottom, each horizontal line is called a period. Each period represents the number of electron shells the element's atoms normally have. For example, there are 4 electron shells in an atom of calcium, so it lies in period 4. Meanwhile, an atom of barium in period 6 has 6 electron shells. As you read across the table from left to right, the vertical lines of elements are called groups. Elements in a group have the same number of electrons in their outermost electron shells. These outermost electrons are called valence electrons, and they dictate how elements interact. Elements in the same group generally interact with other elements in similar ways. None of the elements greater than atomic number 83 are completely stable. All of these elements, including radium, are radioactive. All alkaline earth metals reside in group 2 because they each have 2 electrons in their outermost electron shell. Because atoms need 8 electrons in their valence shell to be stable, the 2 valence electrons in the alkaline earth metals makes them unstable. Nearly as unstable as the alkaline metals, which only have 1 valence electron. As a result, the alkaline earth metals easily lose their 2 electrons during chemical reactions. And as you move from beryllium to radium, the atoms' hold on their valence electron becomes weaker, making each alkaline earth metal more reactive than the one before it.
Moving forward. Okay, I'm going to pause here at transition metals. Good deal. I can do that. And I can